Hello everyone, welcome back to the channel. Today we are going to perform a basic system monitoring practical on Windows. We will monitor CPU, memory, and disk usage using Task Manager and Resource Monitor. This is one of the most fundamental practicals for IT support, system administration, SOC operation, and troubleshooting. By the end of this practical, you will understand how to identify resource consumption and troubleshoot system slowdowns in real time. First of all, why monitoring matters. In enterprise environments, continuous system monitoring help administrators identify performance bottlenecks, abnormal processes, high resource usage, memory leaks, and disk related issues. Monitoring is also important in cybersecurity because malware often consumes abnormal CPU, memory, networks, or disk resources. Task Manager is one of the most commonly used Windows monitoring utilities. It provides real time visibility into processes, performance, startup applications, users, and system resource utilization. This section displays all active processes and their resource consumption. Administrators often use this view to identify resource heavy applications or suspicious processes. For example, if a specific application consumes excessive resources, administrators can terminate the process to stabilize system temporarily. As we end the process, resource utilization decreases immediately. Now we are inside the CPU performance section of Task Manager. This area provides real-time visibility into process utilization and overall system workload. CPU monitoring is extremely important because the processor is responsible for executing instructions for application services and operating system operations. The utilization percentage represent how much processing power is currently being consumed by the system. In this case, the CPU is operating at approximately 10% utilization. A low percentage usually indicates the system is under light workload, while consistently high utilization may indicate heavy processing activity or performance bottlenecks. For example, during antivirus scans, gaming, virtualization, or data processing tasks, CPU utilization may increase significantly. The CPU graph displays CPU activity over the last 60 seconds. This helps administrators visualize workload fluctuations and identify success spikes in processor usage. Here we can observe moderate variations in utilization, indicating active system operating occurring occur. Here we can observe moderate variation in utilization, indicating active system operations occurring in real time. Performance graphs are useful for identifying recurring spikes, unstable workloads, or resource intensive application. The current speed value represents the processor's active operating frequency at this moment. In this case, the CPU is currently operating at approximately 2.16 gigahertz. Moderate processors dynamically adjust clock speeds depending on workload requirement, thermal condition, and power management. When workload increases, the processor may automatically increase frequency to deliver higher performance. The base speed represents the processor's standard designing operating frequency under normal condition. This serves as a reference point of expected processor performance. Depending on workload and power optimization, the actual speed may operate below or above base frequency temporarily. Modern CPUs use technologies such as boost clocks and dynamic frequency scaling to optimize performance and efficiency. The processes count represent the total number of active application, services, and background tasks currently running on the system. Each process operates independently and consumes system resources such as CPU time and memory. For example, browser, antivirus software, system services, and monitoring tools all run as separate processes. Threads are smaller execution units running inside processes. A single process may continue multiple threads performing different tasks simultaneously. This enables multitasking and parallel execution within applications. For example, a browser may use separate threads for rendering web pages, handling audios, running scripts, and managing network activity. Handles represent references that processes use to interact with system resources such as files, registry keys, windows, network connections, or devices. In simple terms, handles helps window manage access to operating system resources. A very high or continuously increasing handle count may sometimes indicate software instability or resource leaks. The uptime value represents how long the operating system has been running since the last restart. This matrix is useful during troubleshooting because prolonged time may sometimes contribute to memory accumulation or resource degradation. In enterprise environments, administrators often monitor uptime when diagnosing stability or performance related issue. Stockades core logical processors. Here we can observe processor architecture details. The system currently contains only one CPU socket with 8 physical cores and 16 logical processors. Logical processors are created through technologies such as simultaneous multi-threading, allowing the CPU to process multiple execution threads efficiently. Virtualization support is currently enabled on this system. This feature allows the system to efficiently run virtual machines and hypervisor based workloads. This is especially important in a cybersecurity lab, SOC environments, and malware analysis setups where virtualization is commonly used. Cache. CPU cache is highly speed memory located inside the processor used to store frequently accessed instructions and data. Cache memory improves processing efficiency by reducing the need to repeatedly access slow system RAM. Overall, the CPU performance section provides administrators with a real-time operational overview of process workloads, system activity, and performance behavior. These metrics are extremely important for troubleshooting, performance optimization, and infrastructure monitoring. Now, I am going to intentionally generate CPU loads to observe real-time utilization changes. As you can see, CPU usage increases dynamically when additional workloads are introduced. This is exactly how administrators identify resource intensive activities. Now we are monitoring system memory utilization. Memory, also known as RAM, stores actively used applications and data for fast access by the processor. Efficient memory management is extremely important for overall system responsiveness and multitasking performance. This graph displays real time memory usage over the last 60 seconds. It helps administrator observe memory consumption trends and identify sudden increases caused by application or background processes. In this case, memory utilization is relatively stable with moderate system usage. At the top right corner, we can observe the total installed physical memory available in the system. This system currently contains 16 gigabytes of RAM. Physical memory directly impacts multitasking capabilities and application performance. Systems running virtual machines, browsers, security tools, or large applications typically require higher memory capacity. The in-use value represent memory currently being consumed by the operating system running applications and background services. In this case, approximately 9.2 gigabytes of RAM is actively being utilized. The available memory represents memory currently ready for immediate allocation to application or processes. In this case, approximately 6 gigabytes of memory remain available. If available memory becomes critically low, the operating systems may start relying more heavily on virtual memory stored on disk. Cache memory contain recently accessed data temporarily stored for faster future access. Windows intelligently uses unused RAM as cache memory to improve system performance and responsiveness. Cache memory is not wasted memory because Windows can quickly reallocate it when applications require additional RAM. Committed memory value represent total virtual memory reserved by application and the operating system. This includes both physical RAM and paging file allocation. If memory demand exceeds physical RAM capacity, Windows may utilize the paging file stored on disk. Page pooled and non-page pool. The page pool contain kernel memory that may be temporarily moved to disk when not actively required. The non-page pool contain critical kernel memory that must always remain inside physical RAM. Administrators often monitor these values during advanced troubleshooting of drivers, kernels, memory leaks, or system instability. The speed value represents memory transfer rate. Higher memory speed may improve data access performance and overall system responsiveness. This indicates that both available memory slots are currently populated. Hardware reserved memory is allocated for hardware level operations such as integrated graphics and firmware functions. This portion of RAM is unavailable for normal application usage. Memory composition bar provide a visual representation of how RAM is currently allocated across active usage and available memory regions. This helps administrators quickly evaluate overall memory pressure. When available memory becomes too low, Windows may increasingly rely on virtual memory, which is significantly slower than physical RAM. This can lead to reduced system responsiveness and application slowdown. In an enterprise cybersecurity environment, SIEM tools, endpoint protection platforms, and virtual machines may consume sustainable memory resources. Overall, memory monitoring helps administrators identify RAM bottlenecks, excessive resource consumption, and potential performance degradation. As more applications are opened, memory usage increases in real time. This helps administrators determine whether a system requires memory optimization or hardware upgrades. Now we are monitoring disk performance and storage activity. Disk monitoring is extremely important because applications and operating system processes constantly read and write to storage devices. This section helps administrators identify storage bottlenecks, excessive disk usage, and slow response behavior. The active time percentage represent how busy the storage device currently is. In this case, the disk is operating at approximately 7% activity. Higher active time indicates increased read and writes operations occurring on the storage device. If the active time remains constantly near 100%, the system may experience storage related slowdowns. This may occur during antivirus scan, software updates, file transfers, virtualization workloads, or database operations. The disk graph displays real-time disk utilization activity over the last 60 seconds. Visible spikes represent periods of increased storage activity caused by file operations or background tasks. The average response time indicates how quickly the storage device responds to read and write requests. Lower response times generally indicate better storage performance. High response time, on the other side, combined with heavy disk activity, may indicate storage bottlenecks or overloaded disk operations. The read speed value represents how much data is currently being retrieved from storage. Applications, system services, and operating system processes constantly perform read operations while accessing files or loading resources. The write speed value represents how much data is currently being written to the storage device. Examples include logging operations, downloads, temporary files, software installation, and database activity. Excessive write activity over long period may contribute to storage wear or performance degradation. This section also displays total storage capacity and disk configuration details. This system is currently using NVMe solid state drive. This SSD provides significantly faster performance compared to traditional hard disk drives. This improves application loading times, file access performance, and overall system responsiveness. The system disk is identified as the primary system drive containing the operating system and application data. Overall, disk monitoring helps administrators identify storage bottlenecks, abnormal disk activity, and performance related issue affecting system responsiveness. Now I'm generating disk activity by copying files. We can clearly observe increased read and write operations in real time. Resource Monitor provides more granular visibility compared to Task Manager. This is extremely useful for advanced troubleshooting and performance analysis. Now we are inside the CPU tab of Resource Monitor. Compared to Task Manager, Resource Monitor provides much deeper visibility into process activity, services, handles, and system resource usage. This tool is extremely useful during advanced troubleshooting and performance investigation. In the process section, we can observe all active processes currently utilizing CPU resources. Each process is assigned with a process ID, also known as PID, which uniquely identifies that running process inside Windows. The CPU column shows current processor consumption, while average CPU displays long-term utilization trends. thread represent execution units running inside the process. For example, here we can see the Splunk service running with a process called splunk.exe. Splunk uses this process for indexing, searching, and managing log data. This demonstrates how monitoring tools themselves also consume system resources. In enterprise environments, administrators often analyze high CPU processes to identify bottlenecks, unstable applications, or suspicious activity. Services. Below the processes section, we can see related Windows services. Services are background components that continue running even when no user is actively interacting with the system. In this case, the Splunk service is associated with the Splunk kd.exe process. This relationship helps administrators identify which service belongs to which running process. During incident response, analysts often trace suspicious services back to their parent process to understand system behavior. Associate handles. Now we are viewing associated handles. A handle is essentially a reference that a process used to interact with system resources such as files, directories, registry objects, or devices. In simple terms, handles show what resources a process currently has access to. Here we can observe that Splunk process currently have active access to multiple log files, database files, and directories. This helps administrators understand what the process is actively reading or writing. For example, if a process logs a file, consumes excessive resources, or behaves suspiciously, associated handles help investigators identify exact which resources are being accessed. In cybersecurity investigations, analysts sometimes inspect handles to detect malicious file access, persistent mechanism, or unauthorized resource usage. On the right side, we can observe real-time CPU utilization graph for individual processor cores. These graphs help you identify workload distribution across the CPU. If one core remains consistently overloaded while other remain idle, it may indicate inefficient workload balancing. In enterprise troubleshooting, these metrics help diagnose performance bottlenecks, software inefficiencies, and resource contention issues. Now we are inside the memory tab of Resource Monitor. This section provides detailed visibility into how processes are consuming physical memory and virtual memory resources. Compared to Task Manager, this view provides deeper memory analysis useful for troubleshooting system slowdowns and memory bottlenecks. In the processes section, we can observe applications currently consuming memory resources. The working set column represents the amount of physical RAM currently allocated to the process. The commit column represents total committed virtual memory allocated to the process. Application with excessively high memory consumption may reduce overall system responsiveness. Hard faults are one of the most important metrics here. A hard fault occurs when Windows cannot find required data in physical memory and must retrieve it from disk storage or the paging file. Since disk access is significantly slower than RAM access, excessive hard faults can reduce system performance. A small number of hard faults is completely normal. However, consistently high hard fault activity may indicate insufficient RAM or excessive memory usage. For example, if multiple heavy applications are running simultaneously, Windows may start relying more heavily on virtual memory, increasing hard faults. Security monitoring tools, browsers, virtual machines, and SIM platforms often consume significant memory resources in enterprise environments. physical memory bar provides a virtual representation of how system memory is being utilized. Hardware reserved memory is allocated for hardware level operations and is unavailable for normal applications. The in use represents memory actively consumed by running processes and the operating system. Modified memory contains data that must be written to disk before it can be reused. Standby memory contains cached data that Windows may quickly reuse if required. Free memory is currently unused physical RAM available for immediate allocation. Windows Memory Management dynamically reallocates memory depending on workload requirements. On the right side, we can see real-time memory utilization graph. These graphs help administrators identify memory pressure, paging activity, and resource consumption trend over time. Overall, the helps administrators diagnose RAM bottleneck, excessive paging activity, and memory intensive applications. Now comes the disk tab of Resource Monitor. This section provides detailed visibility into disk inputs and output operations occurring across the system. Disk monitoring is extremely important for identifying storage bottlenecks, slow applications, and heavy file activity. In the upper section, we can observe processes currently performing disk operations. The read and write columns display how much data each process is reading from or writing to storage. The disk activity section displays individual file currently being accessed by processes. This provides extremely granular visibility into file level read and write operations. The read column represents data being retrieved from storage, while the write column represents data being written to disk. In cybersecurity investigations, file activity analysis helps identify suspicious file access patterns, ransomware activity, unauthorized writes, or abnormal storage behavior. One of the most important storage metrics is disk queue length. This represents the number of disk operations waiting to be processed by the storage device. If queue length remains consistently high, it may indicate storage condensation or disk bottleneck. Short spikes are normal during heavy file activity. However, continuously high queue length may impact overall system responsiveness. The storage section provides overall disk utilization metrics including active time, available storage capacity, and queue length. The real-time graph on the right side helps administrators visualize disk activity patterns and identify sudden spikes in storage usage. Overall, the disk tab provides deep visibility into file operations, storage utilization, and disk performance troubleshooting. Let us understand a real world troubleshooting scenario. Suppose a user complains about system slowness. The first step is identifying abnormal resource consumption. After sorting by CPU usage, we can identify the process responsible for high utilization. We can then investigate further using Resource Monitor. This is the standard workflow followed by IT support engineers and SOC analysts. In this practical, we monitored CPU, memory, and disk utilization using Task Manager and Resource Monitor. We also performed basic real time troubleshooting by identifying and managing high resource consuming processes. These monitoring fundamentals are extremely important for IT support, system administration, and cybersecurity operations. Thank you for watching the whole practical. If you really found this practical useful, kindly subscribe the channel and follow for watching more practicals moving forward.